easy, simple, informal chain rule proof. So before I do so, I want to introduce what the chain rule is. So the chain rule essentially states that for a composite function f of g prime of x, the derivative of it is going to be equal to f prime, with the input still the same, times the derivative of the inside. Now you can visualize this many different types of ways. For example, let's say that I give you a box. So every box that I give you can be modeled with x. And let's say that for every box I give you, or actually let's say that this would be x. Yeah, sure, that's x. Or actually, let's say u and then x. Let's say u and or I guess g of x would work here. You can rewrite the chain rule as this, where u is equal to g of x, simply because it makes things a little bit easier on the eyes. And let's say that each box I give you gives you 2 apples. Now, algebraically, if you want to express how many apples you are getting instantaneously, this would be the function 2x, essentially. So let's say I am giving you 3 boxes per minute, which would essentially equate to 6 apples per minute. So if you rewrote the function as this is equal to y, actually let's say that that is equal to f of u and that is equal to g of u, then f of g of u would be equal to 3, and the input is u, times 2x, which essentially equates to 6 apples per minute, which is pretty simple to explain. Now the reason being so is because the inner output, as you can see, is a product on the outside, because within each change in the outside, or within each change in the outside, you are also changing the inside by a specific amount, such that when you multiply them together, you get your results. So that is how you simplify it algebraically. There's also things with the wheels, things with the gears that people like to explain algebraically. So you can also model this algebraically, kind of like dy du times du dx, and algebraically these cancel out. But I'm going to go with a formal first principles derivative informal proof. Informal proof. So remember that the formal definition of a derivative is x plus h minus f of x divided by x minus h, all as h is approaching 0. Or actually, sorry, as h is approaching 0, because h is the distance from the two inputs. So if I were to rewrite this algebraically, using the chain rule, we want to find the derivative of f of g of x. This is the same as f of g of x plus h, because again, h is the input here. So that's going to be f of g of x divided by h. But we're going to do something interesting, and we're going to multiply this by 1. And to multiply it by 1, we're just going to multiply it by g of x plus h minus g of x over h. Or sorry, over g of x plus h minus g of x. So note that, again, this is just multiplying by 1, so everything is the same here. So interestingly enough, we can rearrange this variable, and we can move this we can swap these two places by the simple laws of algebra. So let's rewrite this again. That's f of g of x plus h minus f of g of x. Minus f of g of x divided by g of x plus h minus g of x. Now I'm going to need a little bit more space here, so I'm going to erase this top part, and let's move this all the way upwards. So I hope you're following so far. All we did was swap these two because that's what the algebra property states that you can do, divided by h. Well, here is just, guess what, the first principles derivative rule. So that takes the same form as the derivative of g of x. So that would just be equal to g prime of x. So we've proved one part of the chain rule already, but now we got to come to this left side. And interestingly enough, this is actually quite interesting because as x is going to 0, or sorry, as h is going to 0, this term becomes g of x. So as g of x plus 0, that's essentially g of x. So we can rewrite this denominator as something quite interesting, and we can rewrite it as because this part is becoming this part is essentially becoming the h that we see in the original equation. So as g of x plus h minus g of x, as h is approaching 0, then this bottom part becomes g of x, such that this input is dg of x, which is essentially a very, very small change in g of x, an instantaneous change in g of x. And the top part is just the derivative from first principles, which would be df of x. And that is just the derivative notation for Leibniz notation. And the interesting thing about Leibniz is that he understands that derivatives are, I'm sure all of them do, but Leibniz, with his notation, emphasizes that d of something is just a very, very small change in that function, or that it doesn't have to be a function necessarily. It's just a small change in whatever variable you're dealing with. And this is why this is denoted as a variable f of, oh sorry, this should be f of g of x actually. F of g of x. So that just becomes f prime g of x, because as we see here, this is the output, this is the input. So again, just simple things here, and then you just times it by g prime of x that we got from the other side. So really interesting chain rule proof here. It's definitely informal because I believe they use epsilons and precise definitions of the limits to understand it further. But this will be all you'll need to conceptualize the chain rule, which is again a simple property, or simple derivative rule. So